All right, folks, we're going to go ahead and get started with our cybersecurity research presentations. Security is highly relevant as any possible attack on the wireless link, such as false data injection, spoofing, jamming, could lead to disastrous consequences. In this research thrust, CCAT works to secure the CAV ecosystem by simultaneously considering cybersecurity threats posed to CAVs, physical transportation infrastructure, and cyber infrastructure that support CAV operations. Today, we're joined by 4 researchers from 3 universities. And up first is Dr. Yiheng Feng, Assistant Professor of Civil Engineering at Purdue University, and Morley, Professor of Electrical Engineering and Computer Science at the University of Michigan, who will discuss their project addressing safety and security challenges in ML-based AV software stack. Please join me in welcoming Drs. Feng and Morley.
All right. Thanks, Kevin, for the introduction, and thank you all for coming to this session. So the research topic of Morley and my project is regarding to address the safety and security challenge of the AV teleoperation. Right. So there are some cases that AV teleoperation is needed. Right. The first example I give is during the commercial deployments. Right. As long as the automation level has not reached level 5, then under certain scenarios, driving scenarios, that and the AV still needs the human intervention, right? So here is an example on the left picture. And the second example, I want to use MCD 2.0, right? This is a very unique feature of MCD 2.0 is about remote controlling of the AV in MCD test facility. So that, researchers from all over the world don't need to physically come to the MCD to test their algorithms, right? So the video shows here is our collaboration with MCD about 1 year ago. We were running the AV control algorithm at Purdue campus while controlling a real AV in real time in MCD test facility, right? So you can imagine that under such a framework, there are a lot of challenges, right? The first thing maybe you can think of is the communication latency, right? So there's a lot of data transmission between the AV and the remote operator, including the remote operator needs to receive the sensor data from the AV, and also at the same time, the remote operator will also send the control commands. On the different remote operation strategies, right? Sending different levels of command to the AV. This one requires very high bandwidth in the communication network, or it will send a very high frequency of command if we talk about real-time control. Actually, in our previous case, we have to reduce our control resolution from 10 Hertz to 5 Hertz exactly because the latencies between the two networks. Okay, and the second aspect of challenge is from the remote operator or the human factors point of view, right? Comparing with the real world human drivers, so the remote operator usually have limited situational awareness, and also similar as the human. The real drivers, the remote operator may also suffer from the fatigue, distraction, or cognitive overload. So the third aspect we want to touch is from the cybersecurity point of view. Again, because of the wireless communication, right, and the communication channel may be compromised or may be vulnerable to different type of cyber attacks, like including the DOS attack or data spoofing attack, right? The data sent to the remote operator or the data sent to the AV can both be compromised, for example. And also the teleoperator, sometimes, in some extreme cases, the teleoperator can also be malicious, right? So this also present some risks in the teleoperation. So all of these challenges actually pose the significant safety concerns to the remote operation of the autonomous vehicles. So in this project, of course, we're not going to solve all the problems. So our point of departure is we look at the misbehavior from a remote operator, either it's a human or some kind of algorithm. And our goal is to determine and protect against the remote operator's behavior. So what we did so far, again, so we only a few months into this project, so a lot of things that we present today are like work in progress and some preliminary results. So any suggestions and the comments are welcome. So what we did so far is we first developed a driving simulator to mimic this remote operation scenario. And then we developed a trajectory level safety check model to detect the misbehavior from the remote operator and if necessary to suspend the control authority from the remote operator. And finally, we want to introduce how we want to leverage the collaborative sensing from other vehicles or from the infrastructure to improve the situational awareness of the AV and also improve the communication robustness. Right, so this is like the driving simulator we developed. So I think many of you are familiar with this. This is the CALA and Sumo co-simulation. So Sumo is responsible for generating those driving scenarios, and the CALA is responsible for the rendering the 3D environment and serving as the interface to the Logitech driving, the driving simulator. Okay, so then based on this, we designed the two kind of scenarios to mimic the remote operation. So the first one is when the vehicle is approaching a static object. We can assume that it's out of its ODD. We assume it's out of the ODD, and then the driver will, the remote operator will take control of the vehicle to bypass this obstacle. And the second case is a little bit more complicated. While the remote operator controlling the vehicle, there's also an oncoming vehicle from the other direction that may cause collision with the AV. Okay, so the safety track module that we developed is try to monitor the status of the AV and then try to stop the command from the remote operator if it finds some potential collisions. So so for both cases, first we developed a very simple static track model, and so when the remote operator is taking control of the vehicle, and this model will be activated and keep monitoring the status of the vehicle, and based on its current trajectory, current track, and to predict its future trajectory. If the near future trajectory has a conflict with a static obstacle, and then the vehicle will reject the command and try to stop. Okay. So this is the test. So the vehicle was first under the autopilot. This is the CALA's autonomous driving algorithm. And you can see now the remote operator actuated me, tried to take over, and I did not do a good job, and collided into the front vehicle, right? So this is without the safety check. So when we implemented the safety check, the same case, safety pilot first, autopilot first, and then, when I start to take control, so you can see the vehicle was under my control at first, but after a few seconds, when it detects my maneuver has some potential collision with the leading vehicle, and it stops the vehicle automatically. So the second case, right, when we have an upcoming vehicle, so this case is a little bit more complicated. So in this case, we developed two trajectory prediction model. We formulate them as a optimization problem, basically to predict the future trajectory of both the Eagle vehicle, the AV, and also the oncoming vehicle, right? And if the two predicted trajectories have confliction, then also the safety check module will be activated to stop the vehicle. Right, and this is the case. So you can see when I tried to took the control at first. Okay, I don't know why it did not play on the other side, sorry. But you can see the bird's eye view that actually when I started to take over, I still could not really see the oncoming vehicle. So, but when I deviate to the other lane, but it's already too late. And of course, this is the case with the safety check. Okay, this plays on the other side. So you can see that when I tried to control first, the vehicle did not really move. Okay, so you can see the vehicle stop there, did not move because it detects the conflict with the oncoming vehicle on the other side. You can see after this vehicle has passed, now the vehicle started to take my command again. And this time, apparently I did a pretty good job navigating the vehicle back to the original lane, and then it came back to the control by the autopilot. Okay, so if you look at this case, actually here's the assumption under the scenario is that this AV can always detect the oncoming traffic from the other side. This is actually not very realistic, especially given if this AV is stuck behind some obstacle, right? So this is why we think that collaborative sensing can also play an important role in the remote operation of the AVs. If we have some other vehicles or infrastructure can detect the oncoming vehicle and send to the AV, it can further improve the safety track module of the vehicle, right? So to that, so Morley will talk about the remote sensing part. Also, the collaborative sensing part.
Yeah, thanks. Yeah, so as Yiheng mentioned, there's always limitations with just leveraging sensor data from a single vehicle's perspective. So to that end, we could leverage data from other vehicles in the form of collaborative sensing. I also want to mention we are looking at the requirement in terms of communication. It turns out having support from other vehicles can also enhance the communication robustness. So when you do remote operator support, you really need to have a reliable communication channel between the vehicle and the remote operator. But we know that network connectivity is not always guaranteed to be high bandwidth and reliable, low latency. So that's the challenge we have to face to address, right? So with cellular connectivities, I will show you some data later. It turns out the network connectivity, depending on the mobility coverage areas, it highly varies depending on the cellular provider deployment. So we have a project called Harbor, which I will describe in a bit more detail here. And I believe this is very applicable to support remote operation support. So CVP stands for Collaborative Vehicular Perception. So the idea here is that if you look at, traditionally, we can just use a peer-to-peer design, right, called V2V, vehicle-to-vehicle data sharing. So from a ego vehicle's perspective, you have data locally collected from your vehicle alone, but you could potentially benefit from data from other vehicles. How do you share such data, right? Sensing data could be very expensive in terms of bandwidth requirement. So if you just leverage peer-to-peer based data sharing, you can do some local compression to reduce the data size. Then you can send the data to other vehicles, and the vehicle does local processing by merging the data together to improve the visibility. For example, a occluded object might more likely to be detected if you get data from other vehicles. So that's kind of intuitive. So as a result of this, we can have a better coverage, right? So some existing work have already demonstrated by just leveraging just another vehicle, you can already improve the coverage and detecting occluded objects. So another thought is that communication, you can have peer-to-peer communication or V2V, vehicle-to-vehicle, but naturally we have a base station, right? Cellular base station, we have the infrastructure side. So one thought is that we can also leverage the central server to do processing because the vehicle itself has limited computational resources. So here the thought is that we can aggregate the sensing data after compression. We can leverage an edge server to merge the data together, and the edge server has more computational resources. It can do more advanced machine learning, computer vision based algorithm to be able to analyze the data more efficiently and more accurately. So here, this is another kind of a scheme, and it's called V2I CVP design, collaborative vehicular perception. So here the communication method is called V2I, vehicle to infrastructure. So obviously, there are limitations with each mode, right? V2V suffers from the scalability issue, right? So intuitively, you have more and more vehicles, you have to kind of almost n-squared kind of sharing data challenge, right? So naturally, you can just broadcast the data, but on the other hand, even with broadcast, you have limited bandwidth, right? Broadcast wireless medium, you don't always have the available resources. You need to be smart about what data to share. That's not always easy to figure out. Another challenge we face with V2I is that turns out the cellular network coverage is not always uniform. And so this is a trace we collected by driving, and we looked at Verizon and T-Mobile in terms of bandwidth, right? So you can see, depending on the location, one network may have higher bandwidth than the other, right? So around 15, you have only 15 seconds, have only one, close to less than 1 megabit per second for 15 seconds of duration for T-Mobile, where Verizon gives you better throughput. So this is an intuition which tells us that even if you just rely on single provider, obviously rely on multi-providers, you can probably get better throughput. But it's always also the intuition that the V2I or CV2X technology doesn't always guarantee you high throughput and low latency, and which is very critical for remote operation support. So the idea here is, as you can see, is very intuitive. Why don't we have a hybrid architecture which leverages V2V and V2I in a smart way so that we can get better, higher bandwidth when we need and get more reliable communication, right? So this is the key idea is that we have these helpies, which are essentially vehicles that need to be helped by helpers which have the V2I connectivity. So the helpies will use V2V connectivity to reach the helpers to be able to send the data through infrastructure, right? So strategically, we need to figure out how to assign the helpers to the helpies. So here's an example, right? So everyone is using V2I. Obviously, may not always work depending on the cellular data coverage. And if you use the V2V link in a smart way to switch to V2V, and assuming ISP-C has enough bandwidth, uplink bandwidth, then you could just use that to be able to communicate, right? So here's an example where we're just trying to share data in a more reliable way. And this could be talking the data sent to the remote operator who needs that kind of information in order to make the control decision, right? So we have this architecture designed and implemented, typed in a using V2V and V2I hybrid architecture to enable reliable communication. And this is not just communication, it's also computation. So this setup also has the necessary kind of computation, which is computer vision data processing to do perception for the detected objects. So I won't have time to go into detail, but this is a published paper at Census 2024, which has the detailed results. As you can see, there is this the edge part and the helper and the helper and the helpee vehicle setup. And there are different algorithms involved to make sure you have the prioritization to be smart about what data to send and making sure that we are deadline aware to make sure we meet the deadline required for real-time perception. Given lack of time, so I want to just highlight some of the key innovation we have for this work. So one key idea here is that we'll need to identify these performance impacting factors in assigning who are the helpees who are the helpers to help upload the data to the infrastructure. So one naive way is just measure the bandwidth directly, but obviously this is kind of expensive, not always scalable. So our intuition is that we can look at for these kind of factors which are easier to measure, like distance and interference, because with wireless communication, you have to be careful. If everyone's talking at the same time, right, you have these interference issues. So we are looking at basically interference is something that you can passively measure. So basically what we did is that we used these factors to understand, like based on physical distance and the network interference levels, to figure out how to assign helpers to the helpees. And this can be run this heuristic can be run periodically because the network state constantly change, the vehicles move, so therefore it needs to be continuously updated. So we have a algorithm which runs continuously to assign the vehicles who are supposed to upload data on behalf of vehicles who do not have sufficient network connectivity. And this runs by maximizing the overall score, so you can balancing out depending on the data upload needs. The other aspect of this, we have to also be aware of the application deadlines, right? The real-time nature of the task is really critical. So we use NTP to help synchronize, because the synchronization aspect is also critical for making sure that the clock is synchronized. Do I have 5 more minutes? Or? Okay, so I'm just gonna skip ahead to show the evaluation results. And I think what's most interesting is the MCD-based evaluation results. But at high level, we have a reduction of the mean latency to upload the results by 38%. And just the last part is the case study we did using MCD testbed. So in this setup, we are able to detect more occluded objects by leveraging this bridge from CAV-B, which uses CAV-A to be able to send the necessary data to be able to detect an occluded object. Applied to the remote operation context, you can imagine the remote operator wants to be able to see that occluded object in order to make safer driving decisions on behalf of the AV. So with that, I just want to leave you a set of future work items. I won't, given we don't have time, any more time left, I don't want to take away from the next presentation. I will end here. Thanks.
Thank you so much.